Hi, my name is Isabel Andrade, and this is my lab report on motion of a falling object. Throughout this report, I will go over an introduction to the lab, reviewing the purpose of the lab and some essential principles. Then I will analyze the motion of the tennis ball as seen through the video on the tracker. Then I will discuss the computational models created through GlowScript and analyze the difference between the observed and predicted graphs, with a conclusion in the report by answering what-if questions about the lab. So in this lab, I record the motion of a falling object moving vertically and analyze the video using Tracker to observe the position of the object with its corresponding time. The purpose is to analyze how gravity and drag force affect the motion of the object, and then compare the observed and computational graphs, analyzing the position of the moving object between three graphs: an observed graph, a computational model without drag, and a computational model with drag. And from the results of the graphs, the slope between the observed position and the computational model with drag were the most similar, with the computational model without drag being the most distinct towards the second half of the position graph. For this lab, we will be using Newton's second law, which states that an object's acceleration is equal to the net force divided by mass, which allows us to acquire the position and velocity update formulas, which we will use for the computational models. Additionally, we will be using the weight force and drag force, which are the only forces currently acting on the ball. And since the forces do not cancel, it causes an unbalanced force, which creates acceleration. Using the program Tracker, I was able to analyze the motion of the object. The mass of the object was 0.058 kilograms. I chose the axis to be down is negative and up is positive, thus creating a downward slope for my position over time graph. To start my computational model for the graph without force, I set the ball's position vector equal to that of the initial position using Tracker. Then I changed the ball's velocity equal to the 0 vector since the object started at rest. And most importantly, I let the proportionality constant for the magnitude of drag force equal to 0 since we are calculating this model without drag. So now in order to calculate the ball's velocity and position through the while loop, we have to initially calculate what the net force is. And in this scenario, since we're calculating without drag force, the only force acting on the object is weight, which is negative mass times gravity. Therefore, I set our W equal to that formula and then set force of net equal to W. So as we can see from the models, the velocity is constantly decreasing since acceleration from gravity is constant and it's the only force acting on the object. We can also see that the slope of the position graph is not flattening over time. So now to calculate the graphs with the drag force, the initial conditions are the same, with the only big difference being the constant for the magnitude of the drag force, B. In my case, I chose B to be 0.001549, which was calculated through trial and error in obtaining the final position of this graph to be equal to that of the tracker. Now, since there are two forces acting on the object, we now have to calculate for the force of drag as well as the force of weight. And by inputting these formulas, we set force of net equal to weight plus force of drag, which allows us to properly calculate for the ball's velocity and position through the while loop. Through the graphs, we are able to observe that velocity is decreasing at a relatively constant rate in the beginning, but then begins to flatten out in the end. Through analyzing all three graphs together, we can see that the model position with drag lined up well with the experimental position. Any differences in these two graphs can be denoted by the fact that there may be error using the tracker video. Then we can also note that the model position without drag had a steeper slope than the model position with drag and the experimental position, which makes sense since drag is not accounted for, meaning the ball is predicted to fall at a faster rate since there's no force that's counteracting gravity. So terminal velocity is the velocity in which the drag force and gravity are equal, thus creating a net force of 0. From this definition, we can initially denote that the computational model without drag would not reach a terminal velocity because since there is no drag counteracting that gravity force, there will not be a net force of 0 causing a maximum velocity. Then, through annotating the computational model with drag, we're able to see that the velocity graph reaches a flattening at the end of the slope, which means that there is a net force of 0 when terminal velocity is reached. Now, having this understanding of what terminal velocity is, we're able to analyze whether it would be affected if the ball was thrown downward versus being dropped from us. The answer is no. In both cases, the object would be approaching the same terminal velocity regardless of whether it was thrown or dropped. And this is because, as we said, terminal velocity is the net force being equal to 0 due to the drag force and force of gravity being countering each other in an equal state. Thus, they'd be reaching the same terminal velocity, but it could happen that they reach it at different times.